Today we have Abigail Hathway from the University of Sheffield, who's going to give us a talk. Abigail has been a sort of leading light in the ventilation space in the UK for many years, UK and beyond, I should say, and has actually done a really lovely range of work, right from sort of small scale laboratory experiments to measure the amount of mixing that opening and closing doors might induce in a room, right up to the sorts of full scale observational experiments that I think she's going to talk to us about today. So I'm not going to talk for any longer and hand straight over to you, Abigail.
Great, thank you. Thanks for coming, everyone. When Helen asked me to do this, I wasn't quite sure what to talk about, and then I thought, given kind of there's such an interest in ventilation at the moment, particularly in relation to reducing the spread of COVID and the importance of having good ventilation, it might be interesting to present sort of just a range of a few studies I've done over probably the last 10 years looking at ventilation, how people ventilate the space, and a few studies where we've just gone into buildings and seen how they're working, because I think in some of the conversations we lack that understanding of actually what happens in the real life and what are some of the challenges. So it's a bit of a range of topics I'm going to talk about. I'm going to start off with some experimental work in a small single person office, looking at how people use their windows, then start looking at how air moves around larger atriums. We've got a case study at the University of Sheffield, before moving on to other larger spaces, I guess with a background in that sort of more fluids area, quite interested in the bigger spaces and how air moves, which is why it led to these studies. But yeah, looking at bigger areas and how you control those spaces in terms of demand control for your ventilation. And then finally, I'm just going to touch on some work we've got ongoing at the moment, looking at small scale hospitality, which I think is really interesting in terms of that mix of actually understanding how people use their spaces and what they understand. So to start with, I think it's probably about 10 years ago now, but I came into academia with that real interest in how you can model things and how you can predict things, and quickly realize, as I think everyone's very well aware, that predicting how buildings perform is very challenging in terms of getting it to represent reality, and that how people use the buildings is one of the big uncertainties, unsurprisingly. And buildings are, for the most cases, designed for people to be in, and they have to work for them. And sort of aware at the time that there were quite a lot of people trying to better predict how windows were used in buildings to then have a better prediction of the energy performance of buildings when you did energy performance predictions. And I was sort of interested in, well, what does this mean for air quality? Because how people use windows has a big impact on then the indoor air quality in terms of what's coming in from outside and how you're diluting anything that's created inside. But also, a lot of the predictive models that were trying to understand how people open windows were very much related to, indoor air temperature, perhaps humidity as well, picking up on the comfort aspects, but not considering air quality, which fundamentally, if you're opening windows, you're changing that a lot. And I was just sort of interested in that, okay, most air quality parameters you can't sense, so you can see how you wouldn't think this would affect how you use your windows. But on the other hand, we know that kind of high level CO2 makes you feel, groggy, you don't perform as well, it can give you headaches. So there are sort of immediate impacts of some of these air quality requirements. So we looked at, what were the available sort of models at the time trying to predict when people open windows. And this graph just shows some examples of those. They're very much looking at, they did look at some other variables as well, but the main one's usually indoor temperature, unsurprisingly, and then how your likelihood of opening a window increases as things get warmer, which is quite obvious, and studies across the world showing sort of slight differences between them, but sort of roughly the same effect. And we were interested in saying, well, if you sort of added CO2 to the mix, would we see any effect? Don't expect it to be as strong as temperature, because that feels quite intuitive that thermal comfort drives your using of windows. But actually, if you're getting very stuffy in a room, do people think to open a window, or do they, just carry on and don't make that connection the same way you do when you're thinking about thermal comfort? So we ran a couple of studies here, and one was an experimental study where we invited individuals to come to a single person office we told them we were looking at the investigating thermal comfort and their performance on a task in this room that we set up, but equally they were welcome to adjust their own environment. And we gave them some little tests to do in that time, and we had 128 people come in and do this test. And then we basically set the conditions in that room to be either hot, which was 28 degrees C, or comfortable, about 20 degrees C, and then either the sort of ambient CO2, which was ventilated beforehand, so you're looking at around 400 parts per million, or we increased it to 4,000 parts per million using dry ice. And then we combined that with some field work, looking at some sort of real buildings where we had single person offices, and we just monitored what was going on. And so with our experiments, this is sort of an overview of the results. What we sort of saw was, in those sort of 4 different scenarios, people would open their window, because that was something we were kind of concerned that would they actually bother to open the window. But when things were hot, you can see the high temperature of these blue bars shows when people open the window, and the red showing the number of people that didn't open the window. So when people were hot, that they did open the window, but with the high levels of CO2, there was pretty much no effect at all. So we weren't seeing, in terms of how the experiment worked, we were seeing that people were willing to open a window and would come due to their thermal comfort, but they wouldn't really respond to that high levels of CO2. We then asked some sort of questionnaires of these people to see how they evaluated their environment, which I think is quite interesting. So here you can see whether people, how people respond to the conditions in the space, as well as sort of opening or not opening windows. And the dottedness shows when people thought things were stale air. So where you've got high temperature, then people, I'm just going to move my thing so I can actually see all of my key for this graph. I do know what I talk about. So start again. We've got the temperature, what they felt about the temperature, and then what they felt about whether the air was fresh and stale. So the dottiness, if it's got a big dotty one, that said they thought things felt stale, and then red is too warm, blue is too cold. So with the high temperatures, you can see they feel generally too warm, and they also convert that to feeling like the air was stale as well. So the warmth gave that sort of feeling of the air being stale. I think what's interesting though is in the comfortable temperature, you can see there is actually quite a big difference between how stale people thought it was when they felt thermally comfortable. There was an increase in people feeling stale at the higher CO2. And given you can't sense high CO2, it's interesting to sort of think about why that might be. We didn't manage to kind of drill down into this, but there must be something about the space there to see that big jump. But it didn't then result in them thinking to open a window. And we combine this with field studies. And one of the things we're aware of our experiment is we didn't have the sort of funding to be able to get people to come and spend like a day in a room we'd controlled. So people were very much in there for a shorter period, half an hour. So one of our reasons for the field study is, one, to see the sort of real life. So as well as the CO2 going into the air, we'd also get the kind of bioeffluents that go with that. So the BO from people, anything else in their breath. And we weren't measuring that, but it would have been there in terms of what was increasing the carbon dioxide in the air. It's very much coming from people, whereas in our experiments, it came from dry ice. So it was purely the gas. And we were looking at here, basically trying to build a model about how we'd predict this window opening. And I think what's interesting is we split the time down into thinking of an arrival period, so where people first turned up, and then an interim period, which we specified as starting after they've been in the room for half an hour, and then the end period separately. And we found sort of quite different effects depending on whether it's at that arrival period or later in the day. And arrival, I think, unsurprisingly, the difference between that sort of indoor air temperature and your outdoor air temperature really drove that window opening. So you come from cold outside and it's really hot, you feel the need to get some air in. I think that makes a lot of sense, it's quite intuitive. But interesting, in the intermittent period, CO2 did have an effect in our model. It was the one after temperature, so it seemed to have quite a significant effect, really. And this graph just gives a rough indication of how that probability of window opening at your different temperatures would increase with increasing CO2. So with this sort of more realistic scenario, we are beginning to see that effect of potentially more the other bioeffluents that are coming from people at the same time as breathing out CO2, but something there is prompting that opening of windows and giving you a bit more of a probability of them being opened, which I thought was quite an interesting result. And then, can link into how you predict window opening performance in your, building performance simulations and things like that. Oops, what have I done? There we go, back to full screen. So, that was, quite interesting to look at how people will use their single occupancy space. And, ultimately with a single occupancy space, you have one person, but what's of more interest is where you have multiple people in the space and you have larger spaces. And there's kind of a lot more complication happening here, both in terms of your fluid flow, how the air is getting through your space, but also, thinking about how the people sort of interact and who's really driving that change of air in space, and whether, any automated controls are really working appropriately for the people inside the building. And we had an opportunity at Sheffield with our new engineering faculty. So this is our new engineering building. It's called the Diamond because the facade is covered in diamonds. And these images just show you a bit about that building. And so we've got a section here through the centre of the building, and this centre is a big atrium, and it's about 70 metres long, so it's a very long atrium. Each facade to each side has open windows that are on automated control, so they can be opened, both facades, and then the top level we have these roof up strands where along each sort of long side of the building the openings can be opened. And this picture at the top to the left, you can just see those sort of windows at the top, so all those vents can be opened. And then here we just got some images of the inside, so you can see it's sort of the ground floor. We have these sort of pods on big orange legs, so it's a long thin atrium, and then it does have several of these pods sort of blocking the atrium as it goes up. So it's quite a busy atrium in terms of the amount of building there, and that then gives us space for students to work at different levels. In terms of comfort, we have the openings for fresh air to come in, but then each floor has underfloor cooling devices, so that pulls air from the atrium under the floor, where it can be both cooled and heated before being distributed in that space. So that has got a bit of a local temperature control within the top of these open pods, and then there's some sealed off pods within this space as well, so they're more just enclosed spaces that are mechanically ventilated. The image in the section I've shown with the air, blue arrow showing the air, how it comes in through the sides, out through the top. This is your sort of summer design, and the winter design was just to open those top roof up spans so the cold air would drop into the space. It also has the toilets pull air from the atrium into the toilet space before being extracted out. So there is, I guess, a bit of mechanical pull from the surrounding toilets as well that do affect that space. So that's sort of the building space we had, and in the build we had quite a lot of sensors installed, and then separately I received some money from the Royal Academy of Engineering to do an industrial fellowship alongside working with Arup, who'd done the engineering design of the space, which enabled me to go back and do a sort of thorough look at that design, and then how the space actually performed in the end. So we go back and with them understand the performance, and also whether that actually matched the design predictions, and particularly the CFD models, which I'm not going to talk about today. So there's a big thank you on this part for the funding from the Royal Academy of Engineering and for Arup for their input. So during the sort of build, we had sensors put in this atrium. We did have humidity sensors as well, but I'm not going to be showing any of that data, so that's why they're not mentioned here. So as you can see, this just highlights the number of sensors we had on each floor. The atrium is these sort of top floors, level 1, 2, 3 and 4, that is mostly open. Going down to the lower floors, it's there's just sort of a single staircase down, so they're not as connected up in terms of airflow. So we're looking at floors 1 to 4 together as a one large space, and not considering the other spaces below it. The sensors shown here, as you see, the reason they're sort of distributed oddly between floors is largely to the amount of open space on those floors where students can sit. So level 2 is mostly enclosed pods. There's not so much open space there. And these sensors, although this is the number sort of per floor, some are at desk height and some are higher up on the walls, so they are at sort of different heights. So in terms of analysing this, this picture gives a sort of better idea of how we sort of group things to look at it. And we've kind of grouped levels 2 and 3 together just because of there weren't many sensors on level 2, and some of them, I think most of them actually were on tables, which meant they were a bit sort of close to individuals and affected by, you can see that a laptop would be placed right next to a temperature sensor, which would probably affect that temperature sensor. We also found we had sensors stuck to these walkways at the top, and these are glazed walkways, so the interior of them is conditioned, and those walkway sensors are always measured very cold temperatures, so we tutored them separately because I suspect they're actually measuring conduction through that walkway due to the air conditioning happening within, rather than measuring the air within the atrium, which is what we're interested in. And what I would sort of wanted to do was sort of use this opportunity to talk through how this atrium performed, because I think it's quite interesting from a large space. It's a very long atrium and it's naturally ventilated predominantly, and I think it shows how something can work well in reality. And so this just shows you one of the sort of years data that we were looking at. So we had 3 years of data to look at in total, but I'm going to pick out some individual bits to look at because it makes things more interesting and easier to understand. So the reason we picked 2018 was largely because we had quite a hot summer for Sheffield, and not if you look internationally or possibly even down in London, but for Sheffield this is pretty warm. And you can see, I think what's interesting at the bottom is shows the roof openings and the facade openings separately. And what we found was, despite this design condition that I said at the beginning that in winter we'd have the roof openings opening separate to the facade, we found they always open together. And then just to note that the way this sort of sensing is in the building, it does come through the BMS. So part of what we were looking at is the ability to pull information out of BMS systems in order to tell us about the internal environment. So we were dealing with the issues that causes, such as substantial data losses, which we did have a lot of, particularly I think the weather conditions which we got from a rooftop weather station. As you can see from this plot up here, these big gaps are where we just had data outages. So this then sort of shows on that top plot what our internal temperature was like. So we'll look at thermal comfort first, and then we'll go on and look at the sort of CO2 results and see how it performs. And then we're going to focus in on some specific areas of interest in a bit. So you can see how broadly, actually, we had a very warm summer, but the temperature within the space was kept pretty well within a sort of a comfortable condition. It's obviously warm, but it was warm outside, and it's not overheated at any point, which was good to see. And that was also quite interesting because we didn't seem to be doing much night vent, which we'd expect to try and cool the space down at night. Wasn't any obvious night vent. It only meant to be kicking in the day when things got hot, but there is a very large volume of air within that space to absorb the heat. CO2 within the space, I think this was interesting because in winter you can see and from being in the space as well, generally speaking, the facade and the roof openings are shut, even though the design was for those roof openings to be open to provide air. But actually, your CO2 levels stayed below that 1200, usually down below 800 most of the time. So there was ventilation coming into the space. Now, being automated windows, they don't seal perfectly when we're shut, so we suspect that most of that is because you're getting infiltration through those windows, and that you do have a large amount of volume of air in there. And with just that background trickle from the extract from the toilets pulling air from the atrium into the toilets before it's extracted, there's enough then to draw the air through those sort of the tiny sort of cracks you'd have behind the windows, with them not perhaps sealing perfectly. So we estimated an infiltration rate here of about 0.6 to 1 air changes per hour, even when everything was shut, which we estimated because we've got gate data for people entering the space. They then go off to classes in various labs and computer rooms, but we had room book information about what those classes were, what size we were expecting those classes to be. Obviously, there's a big uncertainty there about how many students actually arrived at those classes. So we included that in terms of how we were doing the estimation. And in terms of using the room, the gate information for occupancy, we did find that that is a really nice idea, that you can get a good idea of occupancy from that, but there's a very large uncertainty. If you add up over a day, a week, a few months, how many people are going in and out, it doesn't, you know, it doesn't come to zero. You're ending up with the balance not working. So there's clearly sort of issues with using that approach for your occupancy if you want it for something scientific. But you know, within that, we're able to work some uncertainty into that work to give us a sense of what that infiltration would be, and you're clearly getting it through the facade. So what I thought was interesting though is we were able, because we've got quite a lot of sensors here, we're able to actually look at that variation of space and sort of zoom into particular days and see how it's actually performing. And for kind of a large atrium in the real world, this is a really nice set of data. So I've got pulled out just the cold weather and warm weather to show you some times that I thought really showed how it's working. So this example of our cold weather data, so we've got externally it's about 10 degrees C, and this is all our internal temperature points to start with. And so I've coloured these by the level. As I mentioned earlier, level 4 walkways, this dotted line, because I don't believe that's really measuring the air in the atrium. And then we've got the solid lines, which is our average for each level. And then the lighter lines behind are just showing you each sensor. So you can see that sort of range on it. So you can see these lighter green lines are showing that range on level 3. There's one in the middle is your average for that particular level. So and looking at the averages, you can see this seems like quite a well mixed space. You've got a very similar temperature across all the floors. See sort of a variation when you look at the individual sensors. That's not surprising. As I was saying, quite a few of them are on tables, so they do get laptops put near them, and the pods are controlled for comfort themselves. So sensors within the pods will get that sort of local cooling and heating at this time of year. But broadly across sort of each level, we're getting very similar temperatures. It looks well mixed. In terms of CO2, though, we get this sort of stratification forming. And I think if you look here, you can see even within the variability on each floor, particularly if you look at level 4 CO2 sensors, there's not much variability there, but clearly the levels are a lot higher than you're finding on level 1. And I think this just showed that CO2, as we're breathing it out into the warm air, it's clearly rising up and accumulating at that top level. So they're getting much higher levels up there. We're kind of sure this is because of that stratification and not because of numbers of people, because the number of people and seats and knowing the building where students choose to sit, there's a lot more occupancy at the lower levels, particularly level 1, than there is at the higher level. When as you get up there, quite a lot of it is sealed off space and there's just a small pod for people to sit in the open atrium. So this doesn't seem to be a local effect, very much does seem to be related to that stratification, which is what we saw with the CO2 result, the CFD results as well. And then warm weather, the windows start kicking in, which is when it becomes sort of quite interesting, I think. So you can see that in the warm weather, you've got at the bottom showing you when the roof and the windows open, and that does directly sort of link into what's happening in the space. So just in terms of what warm weather is outside, at night it was still quite cold at 10 degrees C, but it's getting up to 21 degrees C in the day. So as things are warming up, everything's opening, and you can see that that sort of air from outside is flooding into the space and cooling it down. You get sort of quite a rapid change, but it also does change that stratification of the temperature in the space. When things are closed, you begin to see more of a difference across the floors, and as they open, you can see we see a bigger drop at the high levels to start with, as that kind of cooler air is coming in, and presume sort of dropping into the space at that point. So really sort of good examples of how that changes the space and how it changes different parts of the building quite substantially. So you're getting some quite big variation across the space as you're opening those windows. We'll look at more of that in a second. CO2, I think it's particularly interesting to see how that opening the windows does dilute it as you'd expect. You can see the windows opening kicking in immediately. Again, you're getting the high stratification, that CO2 at the top floor, but the windows kicking in brings it down, and you can see you're getting sort of very low levels, and that outside air getting into the space and broadly across the whole building as well. So despite the fact it's 70 meters long, it does seem that the air is getting into the center of the building, and the thought is that the pods actually really help drive the air through, because they're not able to kind of rise up so much near the windows, so they kind of drop lower to the floor to sort of move across the space and into the center. So I think this was sort of mainly related to the thermal comfort side of things, and we were interested in that, how the stratification changed over different seasons. So this was a plot showing all our data from, I can't remember, I think this can't remember this just 1 year, or we did all 3 years. But quite a lot of time points anyway, showing at different temperatures in the space what was the showing us what's the difference between that level 1 temperature and then the upper floor. So this would be the temperature at level 1 for all the points, and then for that kind of red circles on your y-axis, it's showing the temperature at level 2. For the orangey colour, that's the temperature at level 3, and the blue colour is the temperature of level 4. So just a way to visualise that difference across the different levels. And I think what was sort of nice about this is you can see in the colder temperature, it's actually quite similar across the different levels, particularly between level 2 and level 4. Whereas as you're getting hotter, you can see level 4 is increasing in temperature a lot more above those lower levels, which makes you think it's quite hard to manage comfort at these temperatures, where you've got at times nearly a 4 degrees C difference across the building. Level 3 and level 4A kind of kicks out here, and what's going on there. These are most of the sensors here, or these sensors are within the pods, which have that local heating and cooling. So they're kind of being directly affected by that, which would then give you sort of a slightly different effect there compared to the wider atrium. And then I did speak just now about how the temperature changes differently in different parts of the building, and as user control, I think is something we're interested in, but this space is very much automated now. But when it was first built, there was interesting having buttons people could press in the space if they felt too hot and wanted to increase the airflow. And we believe this is what happens here, because in winter, when it was quite cold outside, everything opened, and this was at a time when those sort of buttons were in operation, although they then don't exist any longer. And here you can see how that quickly then basically dropped the temperature in the space, because it was very cold weather. So in this situation, both the windows and the roof lights opened at the same time. So this wasn't in the design plan, and anyone with an understanding of wintilation and fluids would see that with it being warm inside at 24 degrees C, and I haven't put the outside temperature here, but it was a winter time, so significantly colder. All the windows and roof lights opening would lead you to a very significant airflow through the space, cooling it down quite quickly. And what I've done in this plan, this is a floor plan of the building. So this centre space is the atrium, and I've just bubbled the temperature change in 20 minutes at different locations. And the graph at the bottom here just is a graph sort of quick and dirty ones showing each sensor, and you can see how some of them are dropping by a significant amount. So this is on the top floor, which is where I think that the buttons were placed for controlling the temperature. And you can see near the edge, unsurprisingly, a very quick change, a drop of sort of 4 degrees C, but even getting into the center, you're getting quite a large change high up. But more significant was on the ground floor, which again, not surprising with the cold air rushing in from the facade into the space. You can kind of see that really happening in these changes near the facade of like 5 to 8 degrees C, but even within the center of the space, within 20 minutes, you're getting a sort of 4 degrees C drop in temperature. So this was, you know, early on in the days of the building where you're probably just tweaking things to get it right, and clearly opening the facade and the roof lights wouldn't be a design plan, but it's actually quite a nice bit of data to show what happens and how you can flush the air into the building, you know, very well with that buoyancy effect, which we sort of know about in in terms of the theory of what's going on. But this is sort of a real building, and you see how that really happens. Obviously not great for the thermal comfort for a lot of these people in this space, and I think shows that the challenges of giving control to the occupants in spaces like this. Oh, sorry, don't know. Yeah, this is the next slide. So just finally on this, just to get a better feel for the space, really, I'm going to go through these slides. This shows you just an image of the space. This is a 3D image, November, May and July, with the points giving you these coloured balls, the temperature in the space, and the key on the light going from sort of 22 upwards degrees C. And then on the right, we've got the window position. So November, everything kept closed all the time. May, things start to like open and shut. And then July, things sort of kick open and stay open for a long time. And what I'm going to do is step through some different times so you can see how the space changes. So November is, you know, pretty similar temperatures throughout it at most of the time across different parts of the space, and you see more variation in May and July. So this is sort of first thing in the morning when nothing's open. Then as we get to 10 a.m. in the July situation, we've got the facade have sort of kicked open once and then shut again. And then things start to get interesting as we move on to 11 a.m. and we've got things open in both the sort of May and the July situation. So what you can actually see in July is things heating up from that facade. So on the right hand side of this picture would be the east facing facade, so that would get the sun in the morning. And you can see in July the heat spreading into the centre of the space. November is staying pretty consistent in temperature, and May you're getting more of a mix, some hotter points within that sort of centre of the space. And as it goes later in the day, July sort of heating up, May that sort of temperatures varying a bit more yellow and red, more towards the centre of the space. So as that sort of cooler air is coming in from outside, keeping the edges cooler, but the centre getting a bit warmer. So I believe, I know it's a bit difficult to follow in a presentation, but I guess just to try and give you a bit of a feel for the different conditions in the different periods and that sort of variation within the space. So it's kind of quite an interesting study to see how a large space actually performs in reality, particularly compared to the design predictions, which you did very well on. I'm not going to present that comparison now because of time. But I think this was, you know, interesting. One of the questions there is, you know, how do you control a space like that if you've got 4 degrees C temperature difference between the top and the bottom floors in hot weather? How do you manage that in terms of keeping people comfortable? And we had another opportunity to look at large spaces in research program at the moment called AirBods, which is looking at how we can design better ventilation to reduce the risk of COVID spread. It's a very large consortium led by Malcolm Cook at Loughborough, and it's incorporating a lot of modelling work, experimental work and field studies. And the project linked up with the events research program last, I guess it was last Easter that started. This was led by Leora in terms of the field work, and as part of that in Sheffield we looked at the Snooker World Championships at the Crucible. So this is another sort of large space. It's not the same as the atrium in terms of it's not so high, but it is a large volume space. So somewhere you'd expect a lot of variation. So, how can you control a space this large for your comfort and your air quality? I think is quite interesting. And as part of this, we put in to this space 50 CO2 temperature and humidity monitors. Just below the BBC icon in this picture of the snooker at the top, you can see a white box. That's an example of one of our sensors. And we all got quite excited when we saw it on the BBC. We had 50 of them spread around the space. I've got an image, the next slide, that shows you a bit more where they are. The airflow patterns in this space are quite difficult to show in an image. I haven't found a good way of doing it, but it comes into the ceiling. This bottom image, I'm trying to show it, comes down from the ceiling, and then at the front of the stage, there's these two large extracts that run up to the full height of the space. So that's where the air is pulled out. And that was sort of retrofitted a few years ago, and it's largely designed about some of the sort of practicalities in that sort of retrofitting. And I think what was interesting here is that we monitor the space over a lot of different occupancies. The snooker goes on for like 3 weeks. But this is, I'm just going to show you the kind of last day, so when it was very heavily occupied for the final. This is a floor plan on the left, so the little red dots show kind of roughly where the sensors are laid out. It's missing a bunch of them, so there's actually some extra lines back in the seating. But it broadly shows sort of how they were laid out, looking at the difference, across the seating area. So we had quite a lot in there. But what was sort of really interesting about this is when you had that higher occupancy in the space, and we didn't see this so much at low occupancy, you got quite a big difference across that the zone and across the seating in terms of your CO2 readings. So in terms of how much exhaled breath is there. So this chart shows the different rows coloured different colours. So that dark blues are the front rows, B and C, and then the yellow is on the back wall, basically behind the back row, and the orange is actually at the upper level, so that's on the lighting gallery. So that's not occupied by people, but just gives us a bit of a higher level measurement. The black line was the average, and there's some black crosses you might be able to just see, and that's around the extract. So we had a sensor sort of stuck right next to the extract there. And you can see this sort of blue colours is pretty consistently down at the lower levels, and the yellow and orange are up at the high levels. And at times it is nearly 400 parts per million difference. And I think this, we were pretty lucky to be putting in 50 sensors into this space. There's a building owner is not going to have 50 sensors to monitor a space. If you're looking at controlling a system, you might put a handful into a big space, but what's more common is you look at what's happening with the extract air, which was exactly what they were doing here. In the extract, they had a CO2 sensor which was used for demand control ventilation. So as that values went up there, it would kick in with the ventilation as it reached specific values. I think what's interesting here is that these red stars show you the CO2 levels as measured by that demand control system. So these are just points because as they were kind of doing the snooker, they were manually noting down the readings at points in the session at the start and in the middle and in the end. So that's why there's only a few points here. But what you can see is that when it's very busy, you're getting a much lower reading within the extract duct than you are within the space, which I suspect is because our sensors here are very much near the people, whereas there's a lot more air volume in that space, which has probably got much lower CO2 values. So the area above the stage and massive volume of air, and in terms of what's being extracted, is going to be much more well mixed. So if we're looking at dealing with COVID and ventilation for COVID, we have guidance for the amount of CO2 levels that we'd consider as worrying. And the guidance does say it can be difficult to do in large spaces, but I think this really highlights that where you put those sensors in the space, you could be thinking, oh, we're absolutely fine, or you could be thinking, oh, I'm really worried. And how you sort of manage that without a good understanding of the airflow is something that I think needs to be, you know, thought about quite carefully. So I think that's just another interesting example of how that, you know, variation in the space can cause difficulties in terms of how you control the space, but also thinking about that process of the control. Where do you put the sensors in order to actually really understand your space? And perhaps there's a way of looking at something in the extract, but you have a range of uncertainty on that which you might need to respond to. And then just finally, before I wrap up, I did want to touch on a project we're doing at the moment. We're kind of only just starting this, so I don't have many results to present, but I think it's kind of very interesting because we're actually getting in and talking to building owners, because everything I've spoken about in the last two buildings, in order to kind of understand that space, you do need to understand how air moves, you do need to understand ventilation, and for a lot of people that is kind of really difficult, and they, you know, they hear the word ventilation and think, oh, that's technical, I'm not going to think about it. So we're running a project in the moment funded through the Protect study, which is looking at ventilation in small scale businesses, where we are doing sort of a bit of short-term monitoring, but then also interviewing the owners about the barriers they have. And I think what's been sort of interesting here is that just sort of some snapshots of some early data. So you can see the sort of range of conditions we're getting. Big difference with the new build, which has a mechanical ventilation system, and I think also importantly an owner involved in the refurbishment of that who understood the system, versus buildings where, which I think is probably quite common, you've got a mechanical system that's owned by the building owner, and the business owner who's running it day to day doesn't have any interaction with that or any understanding of how it works. You know, spaces we're looking at that have, you know, very little facilities in place for moving the air around, and only the ability to open doors to perhaps increase it, which, you know, might be fine in certain conditions, but where they face the prevailing wind causes massive thermal discomfort and, you know, problems for their business when they open them. So being able to manage that ventilation without significant financial input, you can see being a challenge. We're doing, you know, aiming for 20 venues here. This is just a snapshot of our first few, and not the full, you know, we haven't done the interviews there. This is purely some things you've picked up from chatting to the business owners. But what I'm finding interesting about this is being able to talk to business owners and, you know, the challenges they're facing when you, it's easy to talk about ventilation, but once you also talk about the fact that you've got noise you need to think about with your neighborhood if you're late night, you know, the thermal comfort is actually quite significant because of the prevailing wind coming into the space, and thinking about sort of pest control, then it's quite complicated to take things that have not been thought about in terms of ventilation and improve them without some quite significant financial input. So hopefully in the future I might be able to present more on that study. So that was a bit of an overview of some quite different things, rather than having so I don't have a clear summary, because it was just to give a bit of a taster on looking at how some real buildings work and things you might want to think about in respect to that. I guess probably time for a few questions.
Thank you, Abigail. That was really fascinating, and I think it sort of reflected an incredible breadth of your research interests in ventilation. So I've seen some questions. Well, I say see. I've got one from Karen. I apologise if I'm mispronouncing your name. She's in a shared office, so hence why the questions come in via the chat. The earlier field studies where participants had control over ventilation and where they perceived air quality as stale, did you explore any barriers to opening windows or reasons for not ventilating despite their perception of poor air quality, in brackets stale, i.e. why did they not ventilate if they perceived IAQ as stale? It's an excellent question. I think it was one I was going to ask, a very similar one, so thank you for that.
So that was in the experimental sort of studies. So we chose the room and people came to that room. And we were concerned in setting the experiment up that people just wouldn't open the window because it wasn't their space, which was why we did the comparison of hot temperatures as well. So we didn't explore why, partly because basically we did the study, they filled in the questionnaires while they sat in the room, and they did some other things, and then they went away, and it's only later when we analysed it we noted this difference between the perception and the action. But was kind of interesting that they did open the windows when they felt hot. That was kind of clear that there was a significant effect there, but there wasn't when they were high CO2 levels. And so it felt like there wasn't necessarily a barrier to them open the windows because there was a significant effect. They did open them when they were hot. It was just when it was stuffy, they didn't. This would be different people, but there were 128 people altogether.
Can I ask a follow-up question, hopefully on Karen's behalf? I wondered if timescales played a role in that. You know, we're quite good at sensing temperature over short timescales, and that experiment I think was over 30 minutes, whereas perhaps the stuffiness we're more able to tolerate for a longer period. So even though they knew it, maybe if they had been made to sit in it for 2 hours, I just wonder whether they would have opened windows or not.
And it would. So it's partly why we did the field study, is because there you saw there was an effect of CO2, so it felt like this. But that also combined with the fact that there would be other things affecting the stuffiness alongside the CO2 potentially. That so as well as people, because that CO2 would come from people breathing, potentially also the BO from people, or the raising humidity from being sat there breathing, you know, other aspects which we weren't able to kind of split them apart. It would have been really nice to do these experiments under a longer period. And when we set them up, there was a lot of back and forth about this, because it was a PhD study, so there wasn't really any funding attached to it. So I can't remember what we gave people for coming to do it, but it wasn't very much at all. So I think managing to get that many people, I'm not sure they got anything out of it. So being able to, we kind of felt 30 minutes was probably you could persuade people to do, just to be a good egg rather than anything else.
Yeah, well, I think people outside the community are always amazed when you try and tell them that most of our knowledge on thermal comfort comes from a relatively small set of tests on Israeli soldiers, right? I mean, it's quite extraordinary given that it affects everyone's experience of indoor environments, which is huge. So another question in the chat: does anyone want to take themselves off mute and ask a question directly? Helen McIntyre, perhaps. Otherwise, I'm happy to read them out. I just thought you might like to interact directly. So Helen is interested in the participants knowing that it was a study of thermal comfort, whether that may have influenced their behaviour. She'd be interested to see what happened if, for example, they were told to test different coloured pens or something completely unrelated. So a sort of a distraction technique. I think that's quite, I mean, yeah. What do you think?
Yeah, so what they were doing in there, the reason I didn't say it is I've forgotten what the word is for it. It was like one of these tests for your sort of mental agility tests, sort of things you sometimes get at job when you apply for certain types of jobs, and it
like a sort of
mental performance sort of test.
IQ test, or something similar.
It's got, yeah, so sort of
cognitive
questions was what they were trying to do. And then they did have this test at the end. I guess we did phrase it more around thermal comfort, so that could have affected, you know, when we were sort of setting the test up, we said we were seeing, how they performed on this test according to like thermal comfort and things. I think it's what we said. So that might have affected how they responded in that way. But yeah, it'd be interesting we were struggling with how do we it's meeting the ethics and
Yes, of course.
letting them know they could open a window without kind of like, please open a window.
Yeah.
I can't remember, it was a while ago exactly what our wording was.
Well, it's a bit Schrodinger's cat, isn't it? You want an unbiased test, but they know they're in a test, and so it is inherently biased. So Fred has a question. It's slightly philosophical, I think, but it's worth a quick one. How do we go from sort of the acceptance, at least before COVID, that, you know, even in the early days of COVID, we weren't allowed to use the word ventilation in public communication because it's technical, to a state of, well, as Fred says it, you know, yes, ventilation makes sense to non-experts, and they have a depth of understanding that's frankly, or certainly needed in spaces where they're active in controlling their ventilation.
Yeah, I think so. I think there's kind of quite a lot happening in this space, because sort of, Henry, the work you're doing on schools, you're looking at providing guidance and how people respond to it. We're looking at hospitality and understanding people's barriers, and knowledge is one of them, and we're hoping to extend to look at providing some information in a certain way and see how that helps buildings owners. And I know there's sort of people out there trying to do, you know, videos, things around things as well. I think basically it's the studies that are talking to the people in the buildings to find out what works for them is gonna, and then, you know, responding to that in how we design things. I think it's quite, I know from my point of view, and until recently, you know, I worked a lot with engineers in industry, but I didn't work very much with, you know, other types of people on the ground who are running businesses, or if it was businesses, it was larger businesses with building managers who had a technical background. So it is only recently that there's been that sort of opportunity to engage with more people for me, and I can see that there's absolutely a need to do a lot more of that to understand how to kind of translate what we're doing.
Yeah,
I think even that, if what I've realized is stuff that I've written over the past couple of years that I feel is quite straightforward, and it's not for the general public, because there's a lot of words I've been using for decades, but that's because I did a degree in engineering.
Yeah, thank you. I think I will transition from that sort of very broad question to I'll wrap two questions, one from Barbara and one from Debbie, and sort of into one, and unless anyone adds anything else, I think that's the end of the questions. But you know, the questions are, have you done any studies on air cleaners, either filters or UV, and you know, the potential impact of those on COVID transmission, and to what extent are you trying to follow your work through to providing guidance for building design teams?
So the first question, no, we haven't looked at air filters in any way, what we're doing. Second question, we're at the moment working closely with Sheffield City Council and Environmental Health, so less looking at working with design teams and more looking at people on the ground going in, doing you know, surveys of buildings, and sort of through then connecting to the business owners to look at them understanding and retrofitting their ventilation, so getting guidance for them about how to understand their ventilation and retrofit, and for environmental health officers to better understand their ventilation. I think more interested in the retrofit side than new build in that sort of point, but I guess always looking for opportunities to get this, and particularly now, you know, what we're doing out into having an impact on the ground. So I feel like there's the world in ventilation is changing every day at the moment in terms of opportunities like that. That's why my answer is a bit vague, I think. And yes, definitely looking at doing it where possible.
Yeah. All right. Well, thank you, Abigail. I mean, that's a lovely talk, nice, overview of all the work, or not all, some of the work that you've been up to. And I think, perhaps to end on a positive is that this focus on ventilation, I hope, will mean that, the historic barriers that funding sometimes provided in this space will be lessened, and I think that will be a good thing for us all. So thank you very much, and I'll leave you all to the rest of your days.